Welcome to HC33. Keynote 2. Skydio Autonomy Engine, enabling the next generation of autonomous flight.
I'm excited to introduce now our second keynote. HotChip is always about at least one business keynote. We heard Art's great presentation earlier this morning. And HotChips also has a fun keynote. I'm about to introduce the fun keynote now. We actually are joined by the CTO of a local Bay Area company, Skydio. Skydio is actually super successful in getting drones to fly themselves. We've always been hearing about self-driving cars. They're just around the corner, and we're following that with great excitement. In the meantime, just in our own backyard, based in Redwood City, California, we have a drone company that's actually managed to get drones to fly fully by themselves. And they've been actually so good that they even a month or two ago received a certification from the FAA for beyond vision line of sight flight, so BVLOS. It's the first drone company worldwide to achieve this, and I'm super excited that Abe is able to come here today and share with us the insights on the technology that makes that powers Skydio. A few words on Abe himself. Abe is CTO and co-founder of Skydio. He started getting into autonomous flight back at MIT, where he was studying in 2007. When he graduated, he actually helped co-found Project Wing at Google. Some of you might remember that. That was in 2012. 2014, he got together with fellow colleagues and founded Skydio, which is now the leading autonomous flight drone maker in the world. Abe is super broadly skilled in a combination of disciplines: computer vision, machine learning, computer architecture, and vehicle design. And then he is actually holds a bachelor degree from UC Berkeley and a MS and PhD degrees from MIT. And I'm really excited to have Abe here today. Abe, please take it away.
Thanks, Ralph, for that kind introduction. It's an honor to be here today, sharing some of the work that we're doing here at Skydio to enable the next generation of autonomous flight. I'm going to start by giving a little bit of background on drones in general, talk about Skydio and how we fit into the picture, and then dive a little bit deeper into some of the algorithms and compute that enables the capabilities that our drones provide. So first, a brief history of conventional drones. Drones trace their lineage back to RC toys, many decades, where initially they were these gas-powered contraptions that people that were very passionate and trained a lot could fly. With the advance of lithium polymer batteries, they become electrified, and the transition that we're seeing sweep across a lot of industries where electrification brings great benefits, allowed them to be much smaller and lighter and more accessible for a wide swath of people. Then with the invention of MEMS IMUs and small low-cost GPSs, people could get access to these sorts of flying hobbies in ways that weren't possible previously. And those are the sort of key enablers for what transition from sort of conventional helicopters to quadrotors, where the basics in stability and control could be handled by the sensors instead of the pilot's fast reaction times. And then, if you added a camera, you got a really exciting media capture platform that is what we think of as drones today. And so, that sparked the imagination of a lot of people, and it was very easy to see that drones hold the promise for a massive positive impact across a really wide variety of use cases. And that's because drones are tend to be 10x more effective and 100x cheaper than the legacy methods that they replace. For cinematography, instead of these ridiculous crane cars that only Hollywood had access to, everyday people can use drones to get amazing cinematic footage of their weekend exploits. For public safety, drones are much easier and safer to deploy than manned helicopters. For inspection of all sorts of critical infrastructure, especially if it's dangerous or difficult to reach areas, you can put a drone out there to look at things instead of risking the life and limb of our inspectors. Unfortunately, the economics of manual drones just don't really scale. It usually takes an expert pilot or even a team of people on the ground in order to fly the drone. And on average, 80%, up to 80% of a drone's program's budget can be consumed by pilot training and their salaries. And that's because the drones are just very hard to fly to get the data that you need. And they're easy to crash. And as a result, you end up putting in more man hours into prepping for the flights than you actually get flight time out. Fortunately, this is a problem that me and my co-founders have been working on for over 12 years, going back to our research at MIT, where our lab was one of the first in the world to get these sorts of small air vehicles to fly around in areas that were confined, didn't have access to GPS or other crutches like that. And we were fortunate to be at the cutting edge of putting as much compute as we could and the sensors to enable that. So in this case, we were able to get a fixed-wing vehicle with a 2-meter wingspan flying around the parking garage in our lab at 20 miles an hour, thanks in large part due to stuffing the biggest computer that we could fit on it at the time onto it. At Skydio, our mission is to make the world more productive, creative, and safe with autonomous flight. And we can do that across a number of different areas, including inspection mapping, where drones can help digitize the physical world with millimeter precision. Situational awareness, where we can risk a drone instead of the lives of public safety and service members. And cinematography, where we can capture amazing moments with a Hollywood film crew that fits into your backpack. And if we follow that evolution that we're talking about before, the addition of this compute hardware is really what allows us to step between sort of what we call the age of manual hardware and autonomous drones. And we believe that the future belongs to these software-driven aircraft, where you can have AI that allows them to navigate safely, enable fully autonomous workflows, and provide seamless and integrated solutions. Another way you can think about that is the transition between manual drones and autonomous drones is similar to other transitions that we've seen in the tech industry. For example, the transition between flip phones and smartphones was really defined by software flexibility, enabling a really broad set of use cases that weren't otherwise previously possible. And with autonomy, you get a similar transition for drones. Existing use cases become much easier and more reliable, and new use cases that were previously impossible are enabled. And so it's been really exciting to see a whole new set of customers that are now enabled to capture amazing footage like what we're seeing here of some of the highlights from our customers over in 2020. Now, on the strength of the products that we've built today, Skydio has established itself as a world leader in autonomous flight technology. We're the first US drone company unicorn, having raised over $340 million from top-tier venture capital firms. We've built a team of over 300 world-class AI, robotics, hardware, and go-to-market individuals. and we're trusted by the US Department of Defense, enterprises, and everyday customers. So now let's take a look at where the drone industry is today and where we expect it to go in the future. Overall, the drone market is, there's about 2.5 million units sold annually. The vast majority of that is in consumer, with federal, enterprise, and state and local taking up a fraction of the volume that consumers have. But if we think about where we are today versus where the potential is, say drones that are just a fraction of the way to where they could be. So that 2.3 million drones that are being sold for consumers today, if we draw some parallels to other users of pictures and video, cell phones at the billions a year that are being sold today are one of their primary use cases is pictures and video. That might be a little bit over optimistic. But if you look at where point-and-shoot cameras were at their peak in 2010, action cameras in 2016, and especially when drones are the size of hummingbirds, they're light, they're cheap, they're easy to use and deploy, we predict there's a tremendous possibility for really transforming much of the media that consumers capture today. On the enterprise side, that 31,000 drones today, if you take a bottoms-up view and you think about all the different places that drones could provide a tremendous impact for their users. Construction is an area where accurate progress reports and visibility into what's happening would be valuable. You think of one drone per 100 workers. Electrical substations need to be inspected and monitored on a regular basis. If you have a drone living in a dock at each of those, think about bridges, transmission lines, farms, active mines, oil pipelines, and other oil wells, cell towers, power plants, building facades, you name it. There's so many different areas that need to be inspected, need to be monitored, need to have that visibility that drones can provide. I think that over the next decade, we'll see at least a couple of orders of magnitude growth in the enterprise market, which is very exciting. And that's going to happen over a number of stages, what we call the arc of autonomy. Today, we're in stage 1 or stage 2, where you need to have somebody on site and in the loop. You have autonomy that can make it much easier and more flexible and lower the barrier to entry, but there's still a person there directly controlling and telling the drone what to do. With stage 2, you can get to autonomous workflows where the person can give high-level instructions for what they would like the drone to do, and then it can autonomously carry that out. But they're still on site, they're still there monitoring it. And while those autonomous workflows can give leverage and drastically reduce the barrier to entry to deploying those, there's still somebody there directly hand-holding the drone. Beyond that, we envision remote operations where a drone can live in a docking station where it can get charged and upload the data it collects to the cloud. People can remotely log in and sort of carry out missions whenever they need to. That can get extended with additional intelligence and autonomy to sort of one person being able to deploy a multitude of drones that can make things faster, get better visibility into the goings-on that happen. And then in the not too distant future, we see that extending into a world where you can end up having these drones be these time-shared devices, similar to sort of a server in the cloud, where you might have the same drone in 1 second, it's scanning, getting a daily progress report for a construction site, and then flies over and captures a kid's soccer game's highlights. And these just become part of the pervasive infrastructure that makes up the fabric of society. And one of the really exciting things about this is that each step along the way, we're able to provide tremendous value for our customers and build on with incremental learnings and feedback that real-world operation provides. This is in stark contrast to other industries such as self-driving cars, where there's obviously a huge market, but until cars are better than the human drivers, the technology is not really valuable, and you don't get that incremental, iterative development process. Now let's take a look into what makes up the Skydio Autonomy engine. Take a deeper dive into some of the algorithms that we employ on our vehicle to enable the capabilities that we have. So at a high level, autonomy means the ability to sort of see, understand, and act in the real world. It may seem intuitive for people where that just comes as second nature, but takes a tremendous amount of computation and detailed algorithms and sensors to make happen for a robot. At Skydio, we've leveraged computer vision as the primary sensing modality for our drones. We chose computer vision because cameras can just provide this incredibly rich view of the outside world. And cameras are getting better, computers are getting faster, at a much faster rate than any of the other sensing modalities that we've seen. And that provides an incredibly rich platform for us to develop the software foundations that enable the autonomous capability of our drones. On our drones, we have a number of cameras. We have 6 4K fisheye cameras that provide a view of the world, such as what you see in the bottom right. That's a somewhat unique scene. It's one where a drone's actually getting attacked by an eagle. Usually we hope that doesn't happen, but for drones and robots operating in the real world, you have to be ready for anything. So computer vision has been an incredibly powerful modality for us, in large part because of the advances in mobile sensor technology that has been driven by the phone market, and combined with the algorithms that our team has been able to develop, we can enable a broad swath of very exciting capabilities. One of the most important of those is the ability to see and understand the geometry of the world around it. And for this, we use a suite of deep networks that can interpret the scenery around the drone and determine how far away things are. On the left here, you see the image from our navigation cameras. On the right, a color-coded depth map of the scene. And one of the really powerful things that deep learning can enable is that it can allow us to train the networks to handle situations that are otherwise very challenging for conventional algorithms, such as very thin structures where even if there's a gap in the data, the context around can allow the deep network to fill in, or blank textureless walls, where again, context is really key. And it's been incredibly powerful for us to have the capabilities that deep learning provides in order to allow the algorithms to continue to operate and improve as time goes on. In addition to sort of understanding the geometry, it's also really important to understand what is out there in the environment. In particular, for cinematography use cases, being able to understand where a person is or the subject that you're trying to follow is key. So this is a video demonstrating some of the subject tracking capabilities. Again, we use deep learning to segment and identify the people and objects of interest in the image. But it goes beyond that to, instead of just having knowledge in the 2D image where the person is, we have to sort of project that out into the real world such that we can take action. And so using the motion, knowledge of the motion of the vehicle, the depth of the subject and where it all, we can understand where they are in 3D such that we can move the drone to keep them in the shot and get great video. This needs to work across all sorts of lighting and other challenging situations in ways that people often don't end up dealing with if you're just trying to do detection on sort of images that a person is composing. And finally, that all needs to come together into a view, a 3D view of the world, where we can build sort of maps that are persistent over time and use those to plan and evolve the state of the vehicle over time and make decisions about what the vehicle should do to get great footage. And we put that all together, and you can see shots like this, where on the left we have the user camera, which is nice and smooth, highlights the action. On the right, we have a view from the navigation cameras and the depth that we're able to encode. So those are some of the sort of foundational building blocks that we use to enable autonomous flight. But one of the really exciting things about drones as a platform is that they have a ton of software flexibility that you can apply to a wide variety of use cases. So a lot of what we've talked about so far has been focused on cinematography. But if you take that same foundation and add another layer of software on top of that, you can create applications that would make it very easy to do large-scale and accurate inspection. And the Skydio 3D scan is a powerful way to do that. So I'll let this video play to show off some of what it can do. So switching gears, let's take a look at what goes into making an autonomous drone. At a high level, you can think of them not too different from a miniaturized software stack that would go into a full self-driving car or a scaled-up cell phone. What we need is an incredibly powerful and flexible processor that can perform the level of computation needed to carry out the autonomous actions. Fortunately, we've partnered closely with NVIDIA and Qualcomm to develop an incredibly powerful computer that can fit into a small drone. That computer actually has two main SoCs. We have one dedicated to imaging and one dedicated to navigation. In the future, hopefully, we'll have systems that are powerful enough that those can be combined into one and reap the size, weight, and cost advantages of that. But for today, to get the level of imaging performance that drones demand, it takes sort of a fully dedicated imaging SoC to enable that. Similarly, on the navigation side, the level of computation is demanding for pretty much any processor that we could envision. So we have our 6 navigation cameras that feed into the navigation processor. The main camera goes into the imaging SoC, and then we have a microcontroller that acts as a brainstem for the system and handles some of the lower rate sensors. And what has enabled this to happen, as mentioned a number of times, is the sort of advancing compute capabilities that have been pushed by the mobile phone market. But unlike mobile phones, one of the key differences is that drones actually have a much larger power budget. One of the common misconceptions in talking about the electronics that go into drone is that power really matters. And that's true to some extent, but drones, in order to fly, take a lot of power. And that means that they have to have very big batteries, such that the power draw of the electronics often isn't as critical. And that's largely due to the sort of power budget that is mostly consumed by the motor. So at hover, while the drone's flying there, it consumes somewhere between 100 and 200 watts for a medium-sized drone. And it does that over the 20 to 40-minute flight time of the drone. And as a result, if you add 1 watt of compute, which is non-trivial, it only reduces the flight time by about 10 seconds. Similarly, adding 4 grams, or about 2 dimes, would reduce the flight time by 10 seconds. And so at the end of the day, usually the final constraint on compute is driven by the size and weight of the computer that you can fit in there. And you have to sort of build the drone around that. And it ends up being sort of a very computationally constrained algorithmic challenge as a result. So let's look at the types of compute. Obviously there's a lot of details that go into sort of making each of the different algorithms on the drone work. But if we think about the types of compute, we can sort of break it down into 5 general buckets. There's sort of the high-level logic, health monitoring that goes into making the drone work. There's some low-level image processing that is pretty standard across any camera system. There's the geometric computations, projecting, warping, and massaging the sort of geometry of the cameras. Obviously, deep learning is really important. And then one area that we see as a great opportunity for improvement in the future is around nonlinear optimization. And that's in particular because if we map those different buckets of compute to the different types of compute resources that are available, high-level logic, throw that on a CPU, makes sense. It's generally not particularly compute intensive. Low-level image processing is very compute intensive, but there's well-trodden paths with ISPs or GPUs and DSPs if necessary. The geometric computations lend themselves pretty well to the per pixel or very dense parallel workloads that GPUs or DSPs can enable. Deep learning, we're not the only ones to have realized that deep learning is incredibly important for a lot of different things. And so there's been a tremendous amount of work that has gone into making optimizing inference for small power-constrained vehicles. And can do that across GPUs, DSPs, or more and more recent dedicated neural accelerators. But for the nonlinear optimization today, that is running on CPU, and in a lot of ways is the one of the single largest users of that compute today. So before diving in there, just touch on deep learning a little bit more. On our drones, we're in flight. We're running 8 different models, and thinking through the systems and how multiple models are operating in parallel is a really tricky and an important part of the overall puzzle that needs to get handled by systems that enable this. And we have a number of different types of algorithms. So things like person detection and segmentation that are sort of more traditional convolutional networks that people are familiar with. Quantization can work great, and that's been where a lot of the focus in the neural accelerators has been, because you can get a lot of efficiency and other gains from that sort of quantization into integers. But for some of the more advanced networks that we deploy, such as for predicting depth and other things, the dynamic range enabled by floating points is really critical. And so, as hardware designers would implore you to think about the sort of general flexibility and the balance trade-offs when sort of making these neural accelerators for future systems. So back to the sort of optimization problem, it sits at the core of many robotic algorithms and for autonomy systems. So for example, visual odometry, simultaneous localization mapping, system identification, model predictive control, all have close ties in other fields such as augmented reality. And at the heart of them, what you end up doing is you're trying to either fit a state to a set of noisy measurements, or you can formulate things as a cost that you're trying to minimize and then optimize. And those can often be formulated as a nonlinear least squares problem. And that is something that is a pretty general building block that we see across a lot of different autonomous systems. Our motion planning algorithm is a good example of this. Its job is to figure out how the rotor rates and the vehicle state should evolve over time and predict that forward into the future. And we do that by using a large optimization problem that jointly solves over 50 different objectives, including the rotor rates, the dynamics and aerodynamics of the vehicle, obstacles in the world, and maintaining a smooth cinematic flight. We've optimized this heavily such that it can run at 500 iterations a second on the CPU to ensure fast dynamic response and smooth flight. But the flexibility there is one of the key bottlenecks in the performance of the vehicle. If we could run it orders of magnitude faster, add significantly more objectives, the embodied intelligence that this algorithm enables would get drastically better, and we would be able to make systems that were much more capable and much more intelligent. So diving in a little bit more, there's generally two steps that end up being pretty compute intensive, and you sort of iterate between them. So a standard formulation is that you iterate between linearizing the problem and then factorizing and solving the matrix. We'll touch on linearizing the problem in a little bit, but those sorts of factorization matrix operations are pretty common, something that have seen a lot of study over time, but as of yet have not bubbled up to the level of importance where dedicated hardware has been developed to enable the efficient solving of them in production systems. And for autonomous systems, there's a pretty wide set of problems that end up getting solved. But usually they end up somewhere in the form of either sort of medium-sized and dense, meaning every entry in the matrix needs to be accounted for, or very large and sparse. And unfortunately, for those two sets of matrix sizes, none of the sort of existing optimization tools on GPU or others tend to sort of handle those regimes very well. But they're incredibly important for autonomous systems. In terms of linearizing the problem, this is an area that we've been investing a lot into speeding up, because oftentimes that linearization was happening numerically on CPU, and that would take a tremendous amount of compute to enable. So at Skydio, we've developed a custom differential geometry library that leverages symbolic computation and code generation techniques to make it much faster to run and faster to write. It allows the developers to sort of describe the problems in high-level symbolic Python code. Therefore, because it's symbolic, we can sort of analytically take the derivatives and other sort of transformations that are necessary to distill it down into the solvable form. We can analytically simplify the expressions, eliminate common sub-expressions, optimize the compute further, and then generate very efficient machine code. So, for the sets of problems that we have on our vehicle, we can often see the sort of branchless generated code executing on the order of, tens of thousands to hundreds of thousands of instructions, straight line with no branching. And that provided an order of magnitude speed up on CPU. But one of the things that we find really exciting is that we think that this formulation can provide a really great way to optimize for other compute hardware. And by combining everything, by standardizing those interfaces, we can generate very flexible and yet very capable system that can be well optimized by different hardware. in a lot of ways, we think that that is one of the key benefits that deep learning provides, is it allows you to specify a problem at a very high level and then distill it down to very optimized hardware execution. So while we're very bullish about the possibility to improve the hardware capability for executing these types of problems, it's really important to consider that autonomous systems are still very early, and software flexibility is incredibly important. For a lot of the challenges that we talked about, such as stereo vision or object detection, we've evaluated numerous systems that people have offered up to us that could provide hardware acceleration of them. But oftentimes what happens is that the hardware gets the abstraction wrong, and it's trying to solve the end-to-end problem, but it doesn't do it well enough. So if you have a stereo matching solution that can do end-to-end, it can be very performant, it can be very efficient, but if it doesn't handle, for example, sun glare, like in this image, that's something that won't really work on an autonomous system. And if it's in hardware in a black box, and we don't have the right hooks and the ability to continue to evolve and improve those algorithms, that hardware is basically useless to us. And so one of the keys is to really make sure that we think through the end-to-end software abstractions that need to get used, and focus on building foundational building blocks that can be effectively composed to make for very capable systems. And so in the future, we hope that there will be a new crop of SoCs that are targeted towards mobile autonomous systems, such as drones, that can operate in the right size, weight, and power budget, can be vastly more powerful, and especially by leveraging the types of accelerations for the problems that we see as really critical. And with that, I will open it up to questions and sincerely appreciate your time. Thank you.
Thanks for the great video. Now we have Abe live here in person. So glad you could join us here today. Thanks for coming out. Jumping right into the first question. And I'll kind of rephrase that a little bit. The question says, can you please compare your drone capabilities with the ones of DJI? Now let's perhaps say, let's generalize that a bit more. You're really coming up with a new class of a drone. So can you sort of talk about how the market is really evolving, drone technology and the market itself is evolving?
Yeah, thank you. That's a great question. The key differentiation for our vehicles is in the software.
If I can interrupt, just go a little bit closer to the mic.
Sorry.
It sounds loud over here, but the audience, it's pretty
Sounds
quiet.
good. Can you hear me now? Great. So the key differentiation and the key difference with our drones is really in the software that allows them to be intelligent and understand what the user is asking them to do. And many other sort of drone companies and sort of the drone industry at large has had a lot of smoke and mirrors about very intelligent autonomy and stuff like that. But at the end of the day, what really matters is the true intelligence. And even if you claim the same sets of features, if they're not actually performing the job in the situations that you need them to do, the intelligence isn't living up to the need. And it's similar to sort of many of the self-driving cars, like on a highway or in simple conditions. It's really easy to make a demo that you have autonomy, but really getting the full set of environments, set of conditions, and working 100% of the time, or 99.9 whatever nines you need, is the key challenge, and that is where Skydio is differentiated, and that our autonomy works.
That's great. Yeah, I wanted to pick up also on your last slide when you said call to action. Please build us better processors. Right? This is a chip company after a chip conference after all. So maybe do you want to spend a minute or two to expand on that? So if you could basically dream up your perfect processor, how would that be different than what you have access to today?
Yeah. I think there's a ton of opportunity. Obviously, getting the right balance of power budget and acceleration and functionality is really important. There's a number of different workloads that we need to address, as well as the the full set of cameras. We have a lot of cameras in our system, more than most systems are today or have today, and being able to sort of process those cameras with different latency and power requirements is really key. And so being able to pull all that into a single fully powerful SoC with the right accelerations is something that we're really excited about and hope will happen in the not too distant future.
So would you look for 2x the compute power at performance at the same power level, or are you looking for a 10x or a 100x?
We have very capable systems today, so it really talks about the types of systems to go to that hummingbird size vehicle that we think can and should exist. Probably somewhere around half, quarter the power and size, and maybe 2x the compute. But in terms of the sort of future evolution of these vehicles, I think 10x would be really nice.
Yeah, well, Moore's law is alive and well.
Yeah.
Some people say it's dead, but it's still ticking along. So what, 2 or 3 more generations, and then we have hummingbird-sized vehicles.
Yeah, it's alive in the key areas that are really important for us. Like as I was talking about in the presentation, we do some stuff on the CPU, but a lot of the work has been getting as much as we can off of these general purpose CPUs into more targeted accelerators that can be really efficient for doing deep learning inference, or and I think one of the key pieces that's missing is these nonlinear optimization problems that currently we have to stick on the CPU, but have a lot of regularity that I think could be exploited for much more efficient, much more powerful processors in the future.
That's great, yeah. Good comments there. Talk about the algorithms a little bit as well. So this conference is, in the last few years, been dominated by machine learning. Mm-hmm. And it's a sea change also for the computer chip industry. Is AI taking over in your space as well? You have your classical DSLAM, and then you have your path planning and et cetera algorithms. Do you see all or most of your algorithms moving over to machine learning? How much classical CV and or other classical algorithms are left?
Yeah, it's a good question. There's today it's a blend, and for a lot of things we see it continuing to be a blend. There's some things that machine learning and sort of deep learning AI are really good at, but there's also an inherent waste in approximating like known physical quantities. So for a lot of computer vision operations, you can throw a black box deep model at it, but there are specific like physical array models that can explain how the image shows up in the world. And a lot of the power and how you get these algorithms to be efficient, and part of that is that we have been optimizing for a very computationally constrained problem. We have been operating in a very computationally constrained environment, makes us sort of like look for those trade-offs. So even if something maybe could be done fully end-to-end with deep learning, exploiting the sort of known physics to do the math explicitly can often allow for much more efficient execution. And that's good for both execution as well as the sort of robustness and generality of the algorithms, because you can understand the physical properties and debug things in much easier if you know the sort of physics of it. So the low-level imaging operations and other things like that, deep learning is totally crushed, like person detection, those sorts of things. Like the hand-tuned systems are have been totally blown away by sort of what you can do with these data-driven algorithms. But I think a lot of the power is in finding the sort of places where they're complementary, and use the machine learning where it's a good fit, and to understand the sort of noise and the stuff that's a little bit uncertain or fuzzy around the edges, but still leverage the structure of the problems to the full degree that we know that they have.
Great. Also, one question about your sensor suite. Lots of discussion always about how far can you go with cameras? When do you need the radars? Where do lidars come in? Any comments?
Yeah, I think in grad school we use lidar, and there's a lot of capability that provides, but for where we are today and the types of sensors that are available, lidars are just orders of magnitude bigger and heavier and lower resolution and more expensive, such that they're not really applicable for sort of the size of drones that we're targeting and are really safe to deploy everywhere. There have been huge advancements in LiDAR, and I think that there's, I don't think we're quite as dead set that LiDAR could never work. But at the same time, like, computer vision is incredibly powerful. Cameras are getting better really fast. Compute's getting better really fast, and our bet has been that we should focus on extracting the rich information from cameras rather than waiting for the LiDARs to get small enough that they could be appropriate for a drone our size. So LiDAR can be a crutch. It's useful in some situations. It's not fundamentally like better per se in a lot of cases.
Great, thanks for these comments. Yeah. Natalia of Cerebras is wondering, do you use simulated data to train and validate your machine learning models, and also how often do you have to retrain the models? Yeah,
so one of the really powerful things and really nice things about having learned models is that it becomes very easy in a relative sense to make improvements. When you see failure cases, you can really try and sort of mine and exploit data that highlights the sort of specific failure modes and work that into your training set and use that to sort of optimize the performance of the drone. And in a lot of ways, that data is really key and one of the sort of most powerful levers that you have to getting the performance you need. And the sort of balancing and care and feeding of that data is really important to getting to the level of performance that we have. So we use all types of data. Simulated is useful. Real data is, there's no getting around needing real data. And you have to sort of bring it all together in the right ways, in the right sort of structures to get to the level of performance that you need.
Great. Some questions on computer architectures. Joseph wants to know what portion of the software that you're using is specific or to NVIDIA SoCs. How difficult would it be to port to other architectures like Umbrella, Intel, Qualcomm, etc.?
Yeah, so it depends on the different pieces of the stack. Like with any, at a very high level, sort of most any algorithm is able to be ported. But when you get down into the details and really try and optimize, there's specific things that you tailor the software to be able to leverage from the CPU. So things like deep learning, NVIDIA has an amazing deep learning compilation library in their TensorRT that executes really efficiently. But plenty of other people also have ways to sort of run inference on their deep networks. So to some extent, that's one of the easier things. Although those other chip companies also need to catch up and get as good at the inference side as NVIDIA has. On CPU, there's various optimizations that are some different levels of portability, and then GPU specific algorithms similarly are could be ported with some work, and depending on the algorithm may run as fast, but that is something that would need to be sort of optimized explicitly.
So some questions on the FAA approval process. Francois from MBR DNA is asking, I guess with all of that AI on board, does your drone still require an FAA Part 107 drone license?
It certainly does if you are flying for commercial use. The way that we think about the AI is really as a pilot assist. It's there to make the job of the pilot more, give them a more expressive language with which to communicate their desires, and make it sort of easier to do their job, which is really to sort of command the mission and make sure that they're operating safely. So the AI in a lot of ways is a pilot assist, and allows them to focus on the stuff that's really important rather than the sort of detailed stick motions with their thumbs.
And here's a follow-on question also from Francois. I assume you're using ADS-B in and out to integrate into our air control? How do you integrate it into your trajectory path, and do you think it's secure enough? And maybe quickly for the audience, explain what ADS-B is.
Yeah, that's a great question. So ADS-B is a standard for manned aircraft to broadcast their location and velocity information such that listeners, receivers around them can understand where they are. And so our general strategy is actually relatively different from that. Our general regulatory strategy is to try and open up the national airspace from the ground up. So instead of starting with these sort of high-flying missions where the drones would be potentially intermixing with manned aviation, we focus on operations where there's very little risk to either people on the ground or in the air. If you're doing a close inspection of a bridge where you're flying under the bridge, you're flying within a few meters of the bridge, if there's a jetliner there, things have already gone wrong. And so the sort of key to the safety story is really around the sort of ability for our drones to get in close to the structures that they're looking at and be sort of fully segregated. And in a lot of ways, those are also the most valuable places. If you want to look for cracks in aging infrastructure or stuff like that, you want to get in close to look at it in high detail. And that's nicely complementary with also being safe from a airspace perspective.
That's great, yeah. Question about battery technology, right? So flight time. So if you could also dream your ideal battery, what would it be like? And also, do you foresee new battery technology options becoming available anytime soon?
Yeah, so obviously battery life is a key performance metric for drones. Battery technology has been getting better slowly over time. I think we keep abreast of various new chemistries and things like that. But our needs for the battery aren't crazy. Like we have slightly higher discharge rates. We care more about sort of safety than some others, and we care a lot about capacity. But in general, our needs are pretty well aligned with most other users, from laptops to cars and everything in between. So we see battery technologies coming down the road, but it's not an area that we're super focused on. And also in part because for a lot of use cases, at the flight times that drones have achieved, you're able to sort of accomplish a full mission in one battery. And so, if you go from 30 minutes to an hour, for many things, you just land with extra gas in the tank, and it doesn't really matter.
Yeah, so a related question from Ian at Anantech. Can you do in-flight charging with multiple drones, hot swap batteries mid-flight?
Anything's possible. That seems like a pretty tall order and would be quite challenging to do well relative to the benefit. I think one of the things that I didn't touch on as much in the talk is the ability for these drones to live in docking stations where they can sort of take off and land and recharge. And I think that's a much better model where the drone can just sort of go back to its nest and recharge and then come back out. And if you do need sort of like constant air time, you can just set multiple up and they can sort of hot swap by having one fly up and just take the place of the old one.
Great. Now, so for some more fun questions, Satoshi of Numa LLC would like to know, in movie creation, can the drone AI autonomously decide the camera angle and the flight route, considering artistic filming?
Yeah, for sure. That is a great question. And I mentioned in the talk the sort of planning algorithms and all the objectives that it's balancing, and the cinematic nature of the shot is absolutely one of those. And that actually ends up being an incredibly important part of the behavior of the drone and why it feels sort of more intelligent than many others, that it moves in ways that are predictable and result in good shots for the user. So the cinematic nature of what it's looking at is really powerful, and also part of why I believe that drones are this sort of next logical step in the evolution of cameras, where you had film, and then you went to digital, and auto exposure and autofocus and all these other sort of enhancements that can be done computationally, but none of them could really change the composition of the shot. Whereas with drones, you can now have the camera be aware of what it's looking at and actually change the composition of the shot to enhance it and make it look better.
Yeah, and John Masters of Red Hat wants to know how soon until we see movies filmed with this. I want a Terminator movie shot with these, right? And you commented there's already movies being shot, so maybe you can expand.
Yeah. If you look at pretty much any movie or commercial that you shot today, like many of the shots are done with drones, in large part because they're just much cheaper than setting up the cranes and booms that Hollywood used previously. Today, many of those are manually flown drones that are just flown by expert pilots because Hollywood can pay for that. But as you go down market from Hollywood blockbusters, there are tons of drones like Skydio drones being used for all sorts of shots, and I think that is an area that we're really excited about in the future, being able to serve more effectively.
But clearly, you talked a lot about inspection, building, railways, and so on, 3D mapping as current focus areas. With this much technology, what other application areas do you envision that your technology can actually unlock or open up?
Yeah. So drones are a very general platform. In a lot of ways, they are just like a flexible compute platform that carries a camera. And so any sort of situation where somebody wants to go look at something or capture imagery, I think is fair game and can be better done with a drone. So we talked about a number of those, but I think we're really excited to see what others use cases people come up with and may surprise us in the future.
Great. Thanks for your time, Abe. I really appreciate you coming out today, sharing these technologies and these insights with us. On behalf of the entire audience, thank you very much.
Thank you. It's been an honor to be here.
So Abe is actually on Slack. He's been reading. He hasn't jumped on responding, so I expect he might jump in and put out some responses. We still have unanswered questions out there. If you want to get in touch with Abe, he's on Slack. Also send him a direct message. Thank you.